Our next lesson, Chapter 8, Estimating with Confidence. The first section is on confidence intervals, the basics. In this lesson, we'll be able to interpret a confidence level, interpret a confidence interval in context of the problem, describe how a confidence interval gives a range of plausible values for the parameter, describe the inference conditions necessary to construct confidence intervals, and explain practical issues that can affect the interpretation of a confidence interval. Our goal in many statistical settings is to use a sample statistic to estimate a population parameter. In Chapter 4, we learned if we randomly select the sample, we should be able to generalize our results to the population of interest. In Chapter 7, we learned that different samples yield different results for our estimate. Statistical inference uses the language of probability to express the strength of our conclusions by taking chance variation due to random selection or random assignment into account. In this chapter, we'll learn one method of statistical inference, confidence intervals, so we may estimate the value of a parameter from a sample statistic. As we do so, we'll learn not only how to interpret or construct a confidence interval, but also how to report probabilities that would describe what would happen if we used the inference method many times. Your teacher has selected a mystery mean value mu and stored it as m in their calculator. Your task is to work together, for example, with 3 to 4 students to estimate the value. The following command was executed on their calculator. The result was 240.79. This tells us that the calculator chose a simple random sample of 16 observations from a normal population with mean m and standard deviation 20. The resulting sample mean of those 16 values was 240.79. Your group must determine an interval of reasonable values for the population mean mu. Use the result above and what you learned about sample distributions in the previous chapter. If you had to give one number to estimate an unknown population parameter, what would it be? If you were estimating a population mean, mu, you would probably use x bar. If you were estimating a population proportion, you would probably use p hat. In both cases, you would be providing a point estimate of the parameter of interest. A point estimator is a statistic that provides an estimate of a population parameter. The value of that statistic from a sample is called a point estimate. Ideally, a point estimate is our best guess at the value of an unknown parameter. We learned in Chapter 7 that an ideal point estimator will have no bias and low variability. Since variability is almost always present when calculating statistics from different samples, we must extend our thinking about estimating parameters to include an acknowledgement that repeated sampling could yield different results. In each of the following settings, we determine the point estimator that we would use to calculate the value of the point estimate. The makers of a new golf ball want to estimate the median distance the new balls will travel when hit by a mechanical driver. They select a random sample of 10 balls and measure the distance each ball travels after being hit by the mechanical driver. Here are the distances in yards. We use the sample median as a point estimator for the true median. The sample median is 285 yards. The golf ball manufacturer would also like to investigate the variability of the distance traveled by the golf balls by estimating the interquartile range. So we use the IQR as a point estimator for the true IQR. The sample IQR would be 287 minus 284, which equals 3 yards. The math department wants to know what proportion of its students own a graphing calculator, so they take a random sample of 100 students and find that 28 own a graphing calculator. We use the sample proportion p hat as a point estimator for the true proportion p. The sample proportion is p hat equals 0.28, which is 28 out of 100. So to answer the question about our mean that we came up with earlier with the mystery mean, how close is 240.79 to mu, and how likely would that be, the closeness that we get for our answer, we must first answer the question, how would the sample mean x bar vary if we took many simple random samples of size 16 from the population? Since the population is normal, so is the sampling distribution x bar. The mean of the sampling distribution x bar is the same as the mean of the population distribution mu. The spread of the deviation x bar of a simple random sample is 20 divided by square root of 16, which equals 5. So now we can take a look at the simple random samples. If we take simple random samples, n equals 20, and here's the population mu with a standard deviation of 20. Here's what the sampling distribution of x bar would look like, and of our mu, which is unknown. To estimate the mystery mean mu, we can use x bar equals 240.79 as a point estimate. We don't expect mu to be exactly equal to x bar, so we need to say how accurate we think our estimate is going to be. In repeated samples, the values of x bar follow a normal distribution with mean and standard deviation 5. The 68, 95, 99.7 rule tells us that in 95% of all samples of size 16, x bar will be within 10 or 2 standard deviations of mu. If x bar is within 10 points of mu, then mu is within 10 points of x bar. Therefore, the interval from x bar minus 10 to x bar plus 10 will capture mu in about 95% of all sample sizes of size 16. If we estimate that mu lies somewhere in the interval from 230.79 to 250.79, we'll be calculating an interval using a method that captures the true mu in about 95% of all possible samples of this size. The sampling distribution of x bar tells us how close to mu the sample mean x bar is likely to be. All confidence intervals we construct will have a form similar to this: estimate plus or minus margin of error. A confidence interval for a parameter has two parts: an interval calculated from the data, which has the form estimate plus or minus margin of error. The margin of error tells us how close the estimate tends to be to the unknown parameter in repeated random sampling. A confidence level C, the overall success rate of the method for calculating the confidence interval. That is, in C% of all possible samples, the method would yield an interval that captures the true parameter value. We usually choose a confidence level of 90% or higher because we want to be quite sure of our conclusions. The most common confidence level is 95%. The confidence level is the overall capture rate if the method is used many times. Starting with the population, imagine taking many simple random samples of 16 observations. The sample mean will vary from sample to sample, but when we use the method estimate plus or minus margin of error to get an interval based on each sample, 95% of the intervals capture the unknown population mean mu. To say that we are 95% confident is shorthand for 95% of all possible samples of a given size from this population will result in an interval that captures the unknown parameter. To interpret a C% or C% confidence interval for an unknown parameter, we say we are, whatever percent we get, C% confident that the interval from wherever to wherever we end up with captures the actual value of the, and then we fill in the population parameter in the context of the problem. The confidence level tells us how likely it is that the method we are using will produce an interval that captures the population parameter if we use it many times. The confidence level does not tell us the chance a particular confidence level captures the population parameter. Instead, the confidence interval gives us a set of plausible values for the parameter. We interpret confidence levels and confidence intervals in much the same way we are estimating a population mean, population, or some other parameter. In this example, we look at a sample size of 100. Our p is 0.5. They use pi for p in this problem, and then we can take different samples with a confidence level of 95%. We want to look to see how close it gets to capturing the true. So we look at doing some different samples. Each time we can see p hat, what it would equal, and we can see how close we would actually be. Here's the mean, and standard deviation is of course not given there, but we can see how it changes each time we do this. And you can also see on the green segment how it's moving according to how close we are to within that confidence interval. According to the Gallup poll on August 13, 2010, the 95% confidence interval for the true proportion of Americans who approved of the job Barack Obama was doing as president was 0.44 plus or minus 0.03. Interpret the confidence interval and the confidence level. We are 95% confident that the interval from 0.41 to 0.47 captures the true proportion of Americans who approved the job Barack Obama was doing as president at the time of the poll. In 95% of all possible samples of the same size, the resulting confidence interval would capture the true proportion of Americans who approve of the job Barack Obama was doing as president. The price we pay for greater confidence is a wider interval. When we calculated a 95% confidence interval for the mystery mean, we started with estimate plus or minus margin of error. Our estimate came from the sample statistic x bar. Since the sampling distribution of x bar is normal, about 95% of the values of x bar will lie within 2 standard deviations of the mystery mean mu. Our interval would be written as 240.79 plus or minus 2.5. 2 times 5. This leads to a more general formula for confidence intervals. It's the statistic plus or minus the critical value times standard deviation of the statistic. The confidence interval for estimating a population parameter then has the form statistic plus or minus critical value times standard deviation of statistic, where the statistic we use is the point estimator for the parameter. Properties of confidence intervals. The margin of error is the critical value times standard deviation of statistic. The user chooses the confidence level, and the margin of error follows from this choice. The critical value depends on the confidence level and the sampling distribution of the statistic. Greater confidence requires a larger critical value. The standard deviation of the statistic depends on the sample size n. The margin of error gets smaller when the confidence level decreases and the sample size n increases. Before calculating a confidence interval for mu or p, there are 3 important conditions that you should check. 1. Is it random? The data should come from a well-designed random sample or randomized experiment. 2. Normal. The sampling distribution of the statistic is approximately normal. For means, the sampling distribution is exactly normal if the population distribution is normal. When the population distribution is not normal, the central limit theorem tells us the sampling distribution will be approximately normal if n is sufficiently large, that is greater than or equal to 30. For proportions, we use the normal approximation to the sampling distribution as long as n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. Independent. Individual observations are independent. When sampling without replacement, the sample size n should be no more than 10% of the population size, the 10% condition, to use our formula for the standard deviation of the statistic. To make inferences about a larger population or about cause and effect, the data collection process must correctly use randomization. If not, our estimates might be biased, and we shouldn't have any confidence that the intervals we calculate will actually contain the value of the parameter we are trying to estimate. It helps ensure that the statistic is unbiased. To calculate the appropriate critical value to use in our confidence interval, we must assume that the sampling distribution of the statistic we are using is approximately normal. If this condition is violated, the actual capture rate of our intervals will often be less than the stated capture rate. For example, if we take samples from a skewed population and calculate 95% confidence intervals, fewer than 95% of the intervals will actually capture the value of the population parameter. It helps ensure that we are using the correct critical value. To use the familiar formulas for the standard deviation of a statistic, the observations in the sample must be independent. If this condition is violated because we are sampling without replacement, then the actual capture rate will be larger than the stated capture rate. For example, if we take samples of size 50 from a population size of 100 and use these samples to construct 95% confidence intervals, more than 95% of the intervals will actually capture the value of the population parameter. It helps ensure we are using the correct formula for the standard deviation of the statistic. Here's a summary of what we've just went over in the first lesson of Chapter 8. In our next section, we'll learn about constructing a confidence interval for the population proportion for P.